We're super excited to welcome back our Gresham Professor of Astronomy, Chris Lintott, to deliver a really hot-off-the-presses lecture about the latest research on asteroids. So, welcome to Chris.
How's it going? It seemed like a good idea. Make it topical, I thought. A spacecraft flew past an asteroid on Sunday. Make it topical, talk about the results. NASA have released one image. And I've got hundreds of people out there wanting to hear about this asteroid. Keep refreshing the browser. Sometimes that's science though, you don't know the results. I'll make something up. Here goes. Hello everyone. This might be an interesting one. I want to talk about asteroids. But before I get there, I want to start with a really simple astronomical question. It's so simple, I'm going to warn you that if you're in the room, I don't want you to call out the answer. I just want you to think about it. The question is, how many planets are there in the solar system? And the thing is, for most of human history, people have debated this since anyone first noticed that there were things in the sky that moved, that didn't move with the stars, that seemed to track around the sky. But for most of human history, I reckon the consensus answer would have been about 7. There's the Sun, Mercury, Venus, the Moon, Mars, Jupiter, and Saturn. These are all the things that we see easily in the sky that move. And therefore, it was remarkable that somewhere around 1750 or so, there'd been enough thought and actually some discoveries which had led people to conclude that the actual answer was 6, that the Sun and the Moon are something else. We've got Mercury, Venus, Earth, Mars, Jupiter, Saturn. There's actually, in here, there's a bit of a period where people start counting the moons of Jupiter and then the moons of Saturn as they're discovered as planets. So that number goes up rapidly until people work out that moons are a different thing. There's lots more detail of this in a marvellous book by Chris North and Stuart Lowe, which you should go and look at online. So 1750, we've got 6 planets. 1779, we find a 7th, the great English planet, Uranus, found by William Herschel, who wanted to call it George, which would have saved a lot of us a lot of trouble. But no, Uranus it is, or Uranus, or that one, occasionally. And then soon after that, 1781, we get the discovery of Ceres, which sits in the gap between Mars and Jupiter, which had been evident for some time. So now we've got 8 planets. In the early 19th century, there's a rush. We get Vesta, Pallas, and Juno, so now we've got 11 planets. Astrea is found about 30 years later in 1845. We still don't have a good image of Astrea, but when you Google it, you find astrologers arguing about what this means for your horoscope, so we'll represent it with that. It means nothing for your horoscope. We're up to 12 planets, then in 1846, Neptune's discovered, and we're up to 13. And shortly after that, because of techniques that had been developed to scan the outer solar system to look for the presence of Neptune, a planet that many suspected was there, we started to find that there were lots more bodies in that gap between Mars and Jupiter. And at this point, the astronomical consensus in 1848 gets us back to our modern-day answer of just 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And those who've been coming to these lectures for the last year and a half will know that we don't need to talk about the period between 1930 and about 2006 when there were 9. Pluto's not a planet, and you can fight me about that later. However, this doesn't mean that those bodies that were found between Mars and Jupiter were not interesting. Those first discoveries, Ceres and Vesta and Juno and all the rest, turn out to be fascinating places. They're relatively large. Here's Ceres and Vesta, the two largest in context. This is in scale next to our own moon. So they're not as large as the moon, but you can see that they are complicated worlds with surface geology, and frankly, you can see there's a bit of a past. They've lived a little in their environment. These images are from a spacecraft called Dawn. I've spent some time mapping both of them, and here's Ceres, and you can just see that crater in the middle with what seems to be ice deposits on the surface, and we think that Ceres actually has ice within it. They're fascinating worlds which are absolutely not the subject of tonight's lecture, because in some ways, though they're not classed as major planets, they're more like the rocky bodies of the solar system. They have histories and complex stories like Mercury, Venus, Earth, and Mars do. And in fact, Ceres is officially classed as a dwarf planet. Tonight's lecture is really about the rest. So this is a visualization from NASA's wonderful Eyes on the Solar System tool, which shows the 1,362,002 asteroids that, as of this morning, we'd catalogued well enough that we could map their orbits and thus place them reliably in space. And so what you can see here is that most of them do indeed cluster between Mars and Jupiter. There's a gap as you move outwards towards Jupiter, and that's because Jupiter's gravity is deeply hostile to the idea of a small asteroid near it. It's, as we say, cleared its orbit. So if you're an asteroid and you stray too close to a giant planet like Jupiter, then you get ejected from the solar system or sent spinning inwards to the inner solar system pretty quickly. And so we've got this relatively stable bout of asteroids. And so I was tempted. I mean, one option for the lecture is that I list the 1,362,002. My two favourites are the asteroid named after Frank Zappa, for example. Jane Austen has an asteroid. There's an asteroid Lintott, which I'm quite proud of. I had all asteroids get a number as well. And for years, I had the number associated with asteroid Lintott as my PIN number. And I was giving a lecture, and I realized two things pretty quickly. One was that I told the audience that, so they now knew my PIN number. And second, that my wallet is in there. So I wish to point out that I've changed it. Most asteroids today don't get names. There are too many of them. But there is an annual ceremony in which people who study asteroids give asteroid names to people they like. So if you know anyone who studies asteroids, you can get a permanent piece of real estate in the solar system. The only rule, and it's a good rule, is no politicians, which I think we can all get behind. And the inspiration for today's lecture is an asteroid that was named after a person. This is asteroid Donald Johanson, all one word, as it was seen by a spacecraft called Lucy back in January at a distance of about 45 million miles. And the asteroid is that little dot in the center there. You can see it moving between frames taken as the spacecraft flies along. Now, this was only discovered in the recent past, but it was realized that it was a target for the Lucy mission, which is on a mission to do a tour of the solar system's asteroids. It will, as presently planned, visit 11 asteroids. Now, most of them are not going to be in that main belt. If we go back to this picture, I talked about the belt of asteroids between Mars and Jupiter, but hopefully you can see there are clusters of asteroids that share Jupiter's orbit. There's some up at the top there, and some on the right down by this surprisingly large grasshopper in the bottom right, not to scale. Such a stupid joke. Sometimes the jokes are for me. Those clusters of asteroids, they're called the Trojan asteroids. They share the orbit of Jupiter. They're in a gravitationally stable place. And we're interested in them because it's sort of a refuge tip that's been filled up over the course of the history of the solar system. So we think that asteroids that have remained relatively untouched from the very early days of the solar system, from the time when the bigger planets like Ceres, but also Earth and Mars and Venus, were assembling out of these smaller bodies, we may have some of those building blocks, the things that produce the solar system, lurking in those Trojan asteroid families. And it's also possible that other exotic types of asteroid may be there. And so Lucy's main mission is to head out to the Trojan asteroids. It will get to its first Trojan in 2027. But along the way, of course, if you go from Earth to Jupiter's orbit, you have to pass through the main belt. And so that's given us a chance to have a look at Donald Johanson. I'm talking about it now because Lucy's encounter with the asteroid happened on Sunday evening at about 6 o'clock British time. So until then, this was more or less the best image that we had of the asteroid. Even a day or two before the encounter, the spacecraft cameras weren't able to resolve this asteroid into anything other than a point of light. In fact, asteroid is about, the name comes from the fact that it's a stellar point of light. And so We could make some guesses about what it was like, but we didn't have a huge amount of information. One thing we did have before the encounter was details of the orbit of this asteroid. And so I can show you that on an animation. So this is slightly complicated. The things you should care about are the blue is Earth's orbit, and then in green, and I guess it's worth noting that Jupiter's orbit is further out here, and then you've got Donald Johanson is this green orbit, and the pink thing is going to be Lucy. So this runs from 2021 in October when we had the launch. Lucy goes outwards, it encounters the Earth and is thrown out into an outer orbit. It comes back, has another encounter with the Earth last year, and then just on Sunday it flew past Donald Johanson on its way out to Jupiter. Oh, I should have explained the name, by the way. So Lucy, the spacecraft, is named after Lucy the fossil, which is a hominid fossil, which for a while was the oldest evidence of one of the ancestors of Homo sapiens found in Ethiopia, and nicknamed Lucy because the paleontologists who found it, of whom Donald Johanson was a leader, played Lucy in the Sky with Diamonds in camp, apparently on repeat every evening. So we ended up with Lucy, the spacecraft, going to Donald Johanson, the asteroid. The logic is that just as the Lucy fossil tells us about human ancestry and about the beginnings of our species time on Earth, so the Lucy mission will tell us about the origins of the solar system and the start of our planet's existence here in this bit of space. Now, there's something special about the orbit of this asteroid, and not just the fact that it happened to be in the way of this spacecraft. The reason we've got a nice classical picture up in the top right is this is Eragon, who I think was daughter of Icarus, perhaps, in legend. I can't remember what the relation is. Minor Greek legendary figure. Somebody can correct me afterwards. But there is an asteroid called Eragon, which has a family of asteroids that share its orbit. Here they all are. So this is looking down on the solar system, and what you can see in that thing, before we get a dramatic ending, is that you can see the shared orbits of everything that belongs to this family of asteroids. And Donald Johanson is one of these. And so the idea is that something happened to Eragon probably about 150 million years ago, so in the recent past, astronomically speaking, which shattered the asteroid, or knocked bits off it, and sent them skimming out into the solar system. And our asteroid, Donald Johanson, is one of that family. So we're visiting one of a family of cousins that we've never seen before. Now, we can do better than just looking at the orbit, because the other thing astronomers could do, if you give them a point of light, I've said it before, that astronomy is a simple science. We make simple measurements really well. And so if you give us a point of light, we can tell you what color it is. And in particular, the color here indicates that the surface of the asteroid might be made of carbon, or at least be carbon rich. And then we can also tell you how that point of light changes over time. We create what's called a light curve. So this is brightness over time. So as time carries on, the asteroid gets brighter and fainter and brighter and fainter. And there are two unusual things about this asteroid. One is that that period of brightening and fading takes a long time. It's about a 251 or 252 day period, so about 2/3 of a year. And that's very slow for an object that we think is small. So something odd is going on to cause it to have that really slow rotation. The other thing is that the difference between it at its brightest and it at its faintest is quite big. In astronomy terms, it's a magnitude, but it really makes a difference for this asteroid. It's the difference actually between it being easy to spot and actually almost invisible even in the world's largest telescopes. And so something's causing this change in brightness. And there are usually two options as to what does this to a small celestial body. This means I can show my favorite slide. It's the only slide in my Gresham lectures I will reuse, I promise, but it's my favorite one. So the two ways that this can happen are illustrated by my friend Luke Downs, like so. So on the left, you have to imagine an elongated object. And if you imagine an elongated object and you're viewing it edge on and then side on, its brightness changes. There's a strong difference between how much of the object that you're seeing. And so if we have an asteroid that's rotating and is elongated, rather something like a pen or something that's doing this, then you can imagine it will make a big difference whether you're looking edge on or side on. So you'd see this change in brightness. We still have to explain why it takes 250 days, but that's one option. The other option is if you have something that's different colors, then as it rotates, you'll see black, then white, then black, then white, then black. What's the joke about a penguin rolling down a hill? Same thing. So those are your two options. And most people thought, because small bodies tend to be one color, and because we haven't seen any change in color, that what we're seeing here in this light curve is a rotating object. This is an artist's impression. This is not a real image. And so this is the kind of thing you get if you have basically a potato-shaped thing rotating. But why is it slow? The Earth, which is much, much, much larger than this thing that's probably a few kilometers across, rotates once a day. This is taking 250 times longer. This is particularly weird if we remember that we think this thing had a violent origin. If something smashed into this larger asteroid, Aragon, and sent these things scattering, you'd expect things to be rotating. And so people have suggested maybe this is telling us about the event that created the asteroid, that perhaps it was more gentle than we expect. Maybe it was the formation of a crater and things slewing off the top. The details are not clear, but it's a mystery. And that is literally everything we knew about this asteroid before Sunday. I should have given this lecture last week and we could all go home now. But we now know a bit more. And to talk about what we know, I need to introduce you to some other asteroids. There's one that Lucy's already visited, one that wasn't planned when it took off, an asteroid called Dinikesh, named after the Ethiopian word for the fossil, Lucy. Here it is. This is the best picture we had of it before Lucy flew past. It's the dot with the circle around it. The circle, of course, was added later. Otherwise, these things would be easy to find. And when we flew past, we got an image from the flyby that showed that this tiny asteroid, which is about 800 meters across, so this is a very small thing. It's actually the smallest asteroid in the main belt that we've ever visited. It has a moon. It has a friend which has been named Selim. And actually, if you look from the different angle, Selim turns out to be two moons stuck together. So the main Dinikesh here is 800 meters across. Selim is about 200 meters, but composed of what's called a contact binary. And to imagine a contact binary, imagine taking two snowballs and pushing them together, and they sort of stick together, like the beginnings of a snowman. That's a contact binary. So we think these are two bodies that collided together gently, and instead of smashing into smithereens, they stuck together. So now the question is, how does a tiny asteroid, 800 meters across, end up producing this sort of moonlet that it's got? We've got some idea. We've seen asteroids break up before. These are Hubble Space Telescope images of an asteroid that never got a name. It was called P2013 R3. It was originally confused with a comet. But what we think happened here is this is an asteroid that started speeding up its rotation. And if you spin an asteroid faster and faster and faster, then it can shatter into pieces. So why would an asteroid spin up? Well, actually, there's a thing called the Yorp effect, which is just great fun to say. The Yorp effect, it stands for the names of the people who invented it, but the Yorp effect talks about the details of how sunlight interacts with an asteroid. And it turns out that over a long period of time, over many millions of years, if you have an irregular asteroid that isn't perfectly round, then just the effect of sunlight can cause a torque and the thing can spin up. And it can even spin up fast enough that it can fall apart. And so maybe when we're looking at Dinikesh and its friend, what we're looking at here is an asteroid that was once one asteroid, and it sped up and it fell apart. And what the lesson is, I think, is that these dots of light that we've studied for 150, 170 or so years, that we thought of as static, boring members of the solar system, the equivalent of the theorists' trace particles that you sprinkle into the solar system and let move under the gravitational pull of the sun and, the proper planets. These have interesting and complex lives. And so even if we find the ones that we think go back to the start of the solar system, we're going to have to understand everything that's happened to them since. So the picture gets much more murky and complicated. But none of that is why you hear about asteroids normally, of course. If you hear about an asteroid on the news, or on TV, or even in a lecture like this, it's normally because they're presented as a threat to us. Because everyone knows that asteroids sometimes hit the Earth. And we know this mostly because we learn in school that an asteroid did for the dinosaurs, right? And I'm really pleased that even astronomers think hard about this. I'm going to show you, and I have not made this up, the actual logo for the European Space Agency's Centre for Near-Earth Defence. So this is a bunch of people based in Italy who are Europe's defence against asteroids who are trying to hit us. This is the logo that they've chosen. And I just think can you imagine being in a budget meeting and you're going down and you're going, I might fund the Mars rover, or I guess going to Uranus seems interesting, or, oh look, yes, the dinosaurs didn't have a space agency yet, we'll keep their budget going. I think that's great. This is why we know about asteroids. And it's true that we now know that the extinction that did for the dinosaurs is we have excellent evidence that it was caused, or at least coincided with, the impact of a major asteroid just off the coast of Mexico. And we know that partly because if you look at that point in the fossil record around the world, you find a layer of material, which you can see with the naked eye if you get a rock from this boundary. And you can see this layer of material which is rich in iridium, which is an element that's not common here on Earth, but is common in many asteroids. So we can actually see the debris from this impact, even in rocks that you can find and collect here in Britain. And it's an amazing leap of imagination to connect that with a catastrophic event and the biological extinction that we know about that happened in the fossil record nearly 70 million years ago. It was an incredible story. But it's also an inspiration to us to keep an eye out for asteroids that might hit us. And this is timely because back in December, we had the most serious asteroid threat that we've ever seen. And I'll show you a threatening image. I don't want you to be disturbed by it. These are the discovery images of the asteroid in question. It's circled in green. The circle was added later. And this asteroid got the name of 2024 YR4. They don't name the threatening ones. Otherwise, can you imagine Lintott on collision course? Run. So when this asteroid was first found, just from these images, it's possible to calculate its future orbit with some degree of uncertainty. And from that orbit, it was calculated that there was a 1% chance that it was going to hit the Earth in December 2032. 1% isn't that bad. It's not. It's interesting, isn't it? If somebody said to you that you had a 99% chance of winning the lottery tomorrow, you've definitely already spent the money. But if I tell you you've got a 1% chance of having some disease, then I think you think differently about it. But still, 1% is significant, but it's not run for the hills probable yet. Normally what happens is that we've only got a few images here taken on a couple of nights. Normally when one of these asteroids is found, it has about a 1% probability of hitting the Earth. More observations are made over the coming weeks, and that probability drops down to basically zero. This time, as December turned into January, the number went up. And it kept going up as we got more observations. As we looked at the asteroid more, the number went all the way up to a 3% chance of hitting us. Which is what? I don't know. It's less than the chance of drawing a particular card from a deck or something like that. It's beginning to get very serious. And this is the most threatening asteroid that we've ever seen. And then, at the end of January, there were observations from the largest telescope in the world, the Very Large Telescope, which was, that's its actual name. At this point, the asteroid was heading out into deep space, and it could only just be seen by our largest telescope. So in these images, which span the course of a few nights, the asteroid is fixed in the middle. So the things you can see drifting are the stars going past, and the thing that's flickering in the center there is the asteroid, which is just coming in and out of being bright enough to be visible. With these observations, the odds of the asteroid hitting the Earth suddenly dropped from 3% to much less than 0.0001%. We were safe. It's a shame for those of us who like asteroids. I was quite enjoying thinking about this. And in particular, I work on a BBC programme called The Sky at Night, and we decided to devote a whole programme to this asteroid just at the time when it was declared it wasn't going to hit us. But as we thought about what to talk about in the programme, I kept having the same conversation with pretty much everyone I met, which was they all had one question about this asteroid. Once they'd established that we were safe, and they remembered that it had gone from a 1% chance to a 3% chance, from astronomers talking about it to the papers talking about it to normal people talking about it, seemed to be the shift from 1% to 2% to 3%. They wanted to know who screwed up. Who had made a mistake originally? When we were telling people there was a 3% chance, they wanted to know what mistake the astronomers had made that they'd now corrected. Because if there'd been a mistake, then could there be another mistake? Could we be wrong now? And actually, when you talk to people who study asteroids, that pattern, this one was more dramatic than most, but that pattern of we find an object, then the odds go up, and then they decrease suddenly is exactly what they expected. And I'm actually just going to show you a clip from The Sky at Night, because I think we found a good way to explain this. You need to know, I think, three things about this clip for your maximum enjoyment. One is that the expert I'm talking to is Dr. Meg Schwam from Queen's University Belfast. That the footballer who kicks the ball, that will become apparent in a second, is my master's student Gabe, who's an excellent machine learning physicist and perhaps a good footballer. He's in the varsity seconds. I nearly called him a terrible footballer live on YouTube, sorry. And football's hard. And thirdly, I was very pleased to get a Talk United scarf on TV. But here is our explanation for why no one has screwed up. And we're just going to start in the middle of the programme. So if we get Gabe to kick the ball towards the goal, at first, we don't have much information about where it's going, whether it's going in or not. Got Talk United in.
Tracking the asteroid after it was first spotted is like freezing the ball just after Gabe kicks it. It might go in the goal, but the goal makes up just one small part of the area the ball could end up in.
So that's your 1%.
For YR4, the odds of hitting Earth were 1%.
Then we get more data.
No, we've got an initial idea of position, right? Right when it's kicked. We have an idea of the velocity, but it can go any direction.
But a little bit later on, we've got more information as the ball heads towards the goal.
Right, because if you could just stop the ball for a second in midair, you now can see more of where it's headed. You have extra information. You have another data point, right? You have another position, another possible velocity.
This additional data narrows the ellipse, removing much of the area outside the goal. The goal now takes up more of the remaining ellipse, and so the odds of a hit go up. Things are getting exciting. For YR4, it was over 3%.
And that's what happened here. We ruled out parts of space where the Earth wasn't, and so the probability of impact went up.
And then if we let the shot play out,
The third freeze frame shows the ellipse has reduced down again. We're now sure the ball will miss the goal. Bad luck, Gabe.
So I think that works pretty well. And for those who are football fans, I could just sum up the experience. That's when you make the noise, oh. That moment where you go from, that might go into, I think that's going, oh no, it's not. So that's what happened with this asteroid, right? And so we now know we're safe. And actually the scientific data looks like that. So here's the possible trajectories from when it was 1%, and then we can run this through. Over time, that shrank. We knew where on Earth it would hit, actually. It would be somewhere south of the equator. And then there was this sudden moment where the ellipse shrinks with the new VLT data, and it's not likely to hit us at all. But it might still hit the moon. There's still a 3% chance it might hit the moon on the 22nd of December 2032, and it's going to be spectacular if it does. So I'm completely in favor of this thing hitting the moon. We won't get more information until 2028. So part of what we have to do to defend ourselves, to prevent ourselves being dinosaurs, is that we have to track these things. And we're getting better at that. The other thing is that we should know what to do when we find one. And people were beginning to talk about what to do when 2024 YR4 was about to hit the Earth. It was about 70 to 80 meters across. That's enough to be what in the jargon is charmingly called a city killer. So it's not going to cause nuclear winter and humanity would be fine, but you definitely don't want it landing on top of you. And so what we would probably try and do is deflect it. And we ran a test of that a few years ago. There's a mission called DART, which targeted a double asteroid, Didymus and Dimorphos. Dimorphos is the target. It's about 200 by 200 by 100 meters. And this is footage, still photos from the DART spacecraft, which had been commanded to collide with the asteroid. And which, importantly, this is the spacecraft itself navigating. So this is new technology. It's not mission control telling it exactly where to go. It told it to acquire the target and hone in on it. And as you can see, this was a strange mission. We were watching a mission control full of people who wanted their spacecraft to destroy itself. And indeed, it did. It banged straight in to Dimorphos and scored a direct hit. But that's the last image, which got interrupted coming down from the spacecraft. But then the important question is, have we made a difference? And immediately, astronomers knew that something had happened, because this was a much more spectacular impact than we expected. From the ground, very little was expected to be seen. But actually, this is a Hubble Space Telescope image, which showed the Dimorphos had grown this tail. There was material that had been thrown up into space. And following it months later, we can see that its orbit around Didymus has been affected. It's now a 33-minute shorter orbit, and so it's moved about 40 meters closer. And actually, the thing has changed shape, whereas before impact we think it was the spheroid, we now think it's a ellipsoid, slightly tilted. And this is the kind of impact that if we'd done this to 2024 YR4 a few years before the impact in 2032, we could have successfully deflected it. So we can now defend ourselves against small asteroids. It's the only natural hazard that we've developed a technology to prevent. And there's a European spacecraft called Hera that's on the way to Didymus to look at the impact, to better quantify what this did, so that next time we can calculate how big a wallop we need to give an incoming asteroid. If you want to know, now, whenever I talk about this stuff, I worry that I'm worrying people, because we are talking about things falling from the sky. So if you are of a nervous disposition and information helps you, then you can go to this web page, the address is in the bottom left, every morning, and this is a live updated list of the things that might hit us. And we saw with 2024 YR4, I think people think there are films like Deep Impact and Don't Look Up and Armageddon where when astronomers find one of these things, they pick up a phone and call somebody wearing military uniform. Or worse, the President of the United States. But it's not like that, because as I've shown in the early observations, we need to coordinate follow-up way before we're sure that an impact is likely. And so as soon as something is discovered that's a threat, it goes on this webpage and we can follow up. And the thing that's most threatening at the minute is this second thing. It's called Bennu. It's a large asteroid. It's about 500 meters across, so much bigger than 2024 YR4. And it's not going to hit us this century, but there's a 1 in 2,700 chance, so 1 in nearly 3,000 chance, that on the 24th of September 2182, Bennu will hit us. The good news is we've been there first. A probe called OSIRIS-ReX went to Bennu and sent us back these amazing images. So on the left is the view of Bennu from the spacecraft. This is a montage of pictures that have been put together. And what you can see is that it's sort of got this shape like a spinning top. Something that's actually apparently likely to be due to our old friend the Yorp effect again. This is the long-term effect of sunlight. But you can also see that this thing, which is a near-Earth asteroid that threatens Earth, isn't really a rock so much as a rubble pile. And you can see that on the right, where this is a sampling arm from the spacecraft that was supposed to pick up a sample. But as it hits what appears to be the surface, it dissolves like a poorly made sandcastle. And so this is really a loose agglomeration of rocks, of pebbles, of something very different from what we thought we were dealing about. And so you can imagine, if near-Earth asteroids are built like this, why DART's impact had such an effect. Because if you slam something into a rubble pile, you get material thrown out, you get a rocket effect, and so you amplify the effect of hitting a solid surface. Now, the point of OSIRIS-ReX was partly to understand what Bennu was made of in case next century we need to deflect it. But it was also to grab samples and bring them back to Earth. And after a dodgy period in which a rock got stuck and they couldn't shut the canister, OSIRIS-ReX returned to Earth just over a year ago. There's the sample after landing. Here's a bunch of confused scientists in a clean room. It took them a couple of weeks to work out how to open the thing, because you don't exactly want to lever it open and have asteroid everywhere. That's bad. Once they did so, they found that there was all of this material just stuffed in the sample, and bits of this have now been distributed to laboratories all around the world for study. And what's fascinating is we're now getting the results of these studies, in particular from Sarah Russell at the Natural History Museum up the road in Kensington and her team, who have been leading some of the analysis. And they found, using devices like the scanning electron microscope that gives you incredibly detailed mineralogy, and I admit I put this picture in mostly because I thought we needed some color after black and white images of fairly black and white things. This is an SEM image that's labeled by the type of mineral that's there. And they found a surprising amount of phosphorus. They found, crucially, that these chemicals are not like we see in meteorites, so it matters that you've gone and got fresh asteroid and brought it back. And they found that in results that just came out the last couple of weeks, well, about a month ago now, they found out that there are salts in this sample. This asteroid formed from a briny environment, like a salt lake that had dried out. And it came from the cold region of the solar system. So this comes from an unknown body that had a salty ocean somewhere in the outer solar system. And somehow it's found itself on an Earth-crossing orbit. So I've already said that asteroids lead complicated lives. One of the stories here, which I think we suspected already, is that things move around the solar system, that we can't just assume that they've stayed put, and that even small bodies, and Bennu's only 500 meters across, may have had the kind of history that we expect on those larger worlds. My premise for getting rid of Ceres and Co. was that they had complicated geology. We're finding evidence for that even on small bodies. And even more excitingly, in results that came out in January, we now know that the chemistry of Bennu is incredibly rich. So, for example, if you take the amino acids, the chemicals which are the foundations of the chemistry of life, then the majority of them, shown here in yellow, have been found in the sample of an asteroid. And even the 5 bases that make up DNA have all been found in this asteroid sample. So we're not saying there was life there. We're absolutely not saying that. But what we are saying is that asteroids which cross the Earth's orbit, which have this complex history, which must, for the last 4.5 billion years, have been colliding with Earth regularly, to such an extent that some people think all the water on Earth, the water that we drink, comes from asteroids, may have brought with them the raw materials for the chemistry of life. So that our planet, and presumably by extension every other planet in the solar system and every other planet in every other solar system, may have been born with the raw materials that you need for life present. I think that's a fascinating and interesting thought, and it amplifies the fundamental question of modern astronomy, which is that the homes for life in the universe are common. The raw materials for life, if this is not just a one-off, must be common. And so therefore we have the question of where life is. So hopefully by this point you've forgotten that this was supposed to be a lecture about Donald Johanson and this one asteroid, because I said that this was the best image we had of it until the flyby on Sunday. And it's my fault that when I planned this, I had good advice that NASA would release a lot of the data that came back from this flyby that took place on Sunday, it's now Wednesday, in time for me to talk about it. What we've got is one image. So I hope you enjoy the next slide, is mostly what I'm thinking. But it is a fascinating image, and if I had to go, I have no inside knowledge whatsoever. Friends and colleagues of mine, people like Carly Howard, who's an expert on the bodies of the solar system and who's helped build one of the cameras on Lucy, are currently in a bunker somewhere in the States arguing. And my guess is the reason we haven't heard more is that the story is more complicated than they thought it was going to be. So here is now the best image of Donald Johanson. This is something that no one in the world had seen until late Sunday night. It looks, yeah, see, it's got a bit of a reaction. That's nice. It looks like a peanut. Let's be clear. Normally asteroids look like potatoes, so that's exciting. The first thing you can see from this image is that this asteroid's bigger than we expected. It's actually 8 kilometers long, which is why it doesn't fit in the frame. I haven't done a bad job of constructing this slide. Now, luckily, Lucy is a modern spacecraft. When we had the Voyager missions to the outer planets, the engineers and the scientists would carefully and painstakingly command the spacecraft individually to take each image. Point here, point here, point here, point here. That meant they had to waste a lot of effort because they couldn't be certain with the spacecraft moving at high speed through the solar system. You couldn't be precisely clear where you had to point, and so they'd have to cover a large area just to make sure that they got the planet in there somewhere. There's a famous result with Halley's Comet when the Giotto probe flew past it, that they'd programmed the thing to look at the bright bit, and it turned out the nucleus was dark and carbonaceous, and it nearly got missed. So Lucy took its own images. It's now got enough intelligence on board that it can target its own camera. So there will be more images coming back that should show the rest of the spacecraft. There's a slight problem, the rest of the asteroid. There's a slight problem in that the camera couldn't point towards the sun. So at closest approach, it stopped taking data to preserve the instruments for the next 9 asteroids. So we've got a bigger than expected asteroid. We can see immediately why it had this big change in brightness, because it's long. And you can also see that it's one of these contact binaries, these snowman-like things where 2 things have collided together. These are 2 separate bodies, and there's a neck down the middle. We're beginning to discover that when we visit small things in the solar system, this is how they seem to form. So, by the way, this is just a rotation, but this is the movement here. Remember, this thing rotates slowly. The movement here is caused by the spacecraft moving as well. But you can really see that neck region. You can almost see what looks like a join between 2 things. And if I show you every small body in the solar system we've ever visited, if you look at the small ones, whether they're Arrokoth in the middle there, that's one of Pluto's neighbors visited by the New Horizons spacecraft, or Tutatis on the right, a tiny asteroid that flew between the Earth and the Moon and was visited by a Chinese spacecraft, or down at the bottom, some of the comets like Halley or Churyumov-Gerasimenko. We see these binaries. It seems like the solar system likes creating these things. And so there's something about how you assemble asteroids out of rubble, out of the primordial matter, that produces these slow collisions. Because if you smack things together, you don't get this sort of form. So it's telling us that this is a sort of gentle process that happens early on. The other thing you can see immediately from this image, and at this point I'm more or less, but this is my guesses as to what we'll find out when the real experts write about this, you can see that there are craters. Craters on a surface normally tell you about age, because if you put a piece of material, a piece of rock out in the solar system and wait, it will eventually get hit by meteorites and asteroids. And the longer you wait, the more craters you get. If you look at the moon, then the seas, the dark areas, have fewer craters than the highlands because they're younger. They're recent lava flows. In lunar history, they're recent. And so it's tempting to look at this and say, look, this larger body on the right has more craters than the one on the left, which is weird. If these things form together, they should have the same cratering record. Now, this is one image. It may just be a trick of the light. So it may just be that we don't see the craters here because the sun is shining down. It's closer to midday over there. So I don't know whether that's a real result. And it may also be, remember, if this thing formed in a violent collision, something hit its parent body 150 million years ago, perhaps the cratering isn't telling us about age, it's telling us about what happened in that violent encounter. So maybe this was closer to the surface or something. I am guessing. The neck region seems to be really smooth. It reminds me a bit, actually, of another one of those bodies, Arakoth, which is this small icy thing that we visited in the outer solar system. This was visited on New Year's Eve, and for a while in the images it looked like a champagne bottle. But we eventually settled on Snowman. But you can see there's that smooth region in the neck. So maybe that's another sign that these things have collided together. This is a closer up image. You could see, I think we're really on the edge of resolution here, but you can see that there are really small craters here. We're seeing things down to about 10 meters. And if you look on the neck, you can see there are some boulders. They're little dots, but those are boulders about the size of the stage or a little smaller. And there appears to have been a landslide. They appear to have rolled down the slope. So something's happened to this thing after it formed. Because for a landslide to happen, you need to have the hill in place. These are all really basic questions. This is what happens when we find a new world and we see it properly for the first time. People will be arguing about this image and whatever other data they've got, and this is the first time that all of Lucy's instruments have taken data, and they did so successfully. People will be arguing about this all the way to Jupiter and back. Way past the next encounter with an asteroid in 2027. But it's still exciting to be on stage and show you something that no one else had seen 4 days ago. I think that's cool. And it reminds me of, I think, one of my colleagues on Sky at Night, person I had the privilege of working with for many years, was Patrick Moore. And apart from being the television presenter who got Sky at Night going in the 50s, he was an amazing lecturer. He was, in fact, the person who gave the first lecture I ever went to at school. He talked about the outer planets. He talked very fast, and I actually don't remember a lot about what he said, apart from 2 things. One is he made sure to say Uranus, because he knew he was at a school. And then the second thing was the last bit of the lecture. He said, look, I've told you what we know about the outer planets, but if I came back in 10 years' time, it would all be completely different. And so I think the best I can do tonight is that I've told you what we know about asteroid Donald Johanson, and if I come back in about 2 days' time, it'll all be completely different. Thank you very much.